For this class, we only need a basic derivative table. We're just taking a quick look at the derivative table before we do the assignment. So there's really only three derivatives in this class. Of course, in Calculus 1, single variable calculus, we have a complete derivative table. It's just basic derivatives required, so we don't need all that for this class. We just go ahead and say it 1, 2, 3. We'll comment on all that in a minute. Yes. So what is a derivative? It's going to be the power rule. Yes, this is the power rule. This is an example. I call it the general power rule. So this is the chain rule here. Yeah. So chain rule, it gets pretty messy. So we'll just erase this. This over here is going to be an example. And this, of course, is the product rule. And on the right is an example of the product rule. So that's basically it. We're literally saying that all we need is the power rule, the chain rule, and the product rule. So in this class, we only do the most basic derivatives. What about the quotient rule? If, for example, we have f of x, equals x plus 2 over x squared. Well, we do know that, of course, we can rewrite that as x plus 2. Yeah, x to the negative 2. In other words, take the x up top as a negative exponent, and then it's the power rule. We're not making a big point here. It's simply true that all quotient rules that exist, every quotient rule, all division in math can be written as multiplication. You take the bottom up top. Every quotient rule is also a product rule. There's nothing wrong with taking using the quotient rule if you need it. I guess yes, in this entire class, we probably don't ever need the quotient rule, but if that ever comes up, you can use the quotient rule, but the quotient rule technically is tied into the product rule. So once again, only three rules: general power rule, chain rule, and product rule. Okay, so all of that being said, calculus 3, you do not need calculus 3 multivariable for this class. You don't need this. We do have to note, we do have to be able to take partial derivatives, some very basic partial derivatives of multivariable functions. We're actually going to do some of that in the homework right now. But these two examples, it's very, very common in microeconomics, actually, that function and that function. Those are two multivariable functions, yes. Once again, multivariable. F is a function of both x1 and x2, and it equals some number a, input 1, that's independent variable 1, to the power of b, plus some number c, x2, that's independent variable 2 to the d, where all letters, of course, are just constants. That's a very, very easy, both of them are very, very easy multivariable functions. So we'll take a look at partial derivatives later. We're going to comment on this at the end, but for multivariable functions, we do need partial derivatives. So let's just jump right into the easy homework here. Okay, so we can discuss the homework, but that would be a little bit silly. We're just going to be taking derivatives here, yeah. So we start with number 1, the easiest of derivatives, yes. Okay. There is kind of a technicality here. It's not that big of a deal. But for example, the natural log of x, yes, the natural log of x, the derivative is d over dx equals 1 over x. We just looked at a table and that wasn't on there. It doesn't matter. Technically speaking, all derivatives are chain rules. If we think of derivatives as functions, all derivatives that exist, f of g of x, a function within a function, take the derivative of it. Yeah, all derivatives that exist are the derivative of the thing multiplied by the derivative of the inside. It's hard to think of things like that as a function within a function, but technically the natural log everything is a chain rule. Technically, we just don't always think of it that way. But anyway, so the first one is kind of hilarious right there. So we have y equals x cubed, that's a. Y prime equals power out front, 3 to the negative 1 equals 3x squared. It's not even really worth our time there yet. Okay, so done with that. So number two, I just want to kind of illustrate something, no big deal. It's just a basic calculus review. We're just having fun. But this is the Leibniz notation. It doesn't matter explicit, implicit differentiation. We learn in calculus, explicit is y equals, that's explicit. Yes, implicit, as we said a moment ago in a video, implicit is where y is not alone. It doesn't matter if y is alone because we have implicit differentiation. I'm just making a simple point. Once we do a lot of derivatives, we understand it doesn't matter if y is alone on the left or if y is not alone. Implicit differentiation and explicit differentiation are exactly the same. I shouldn't even say that because the point is all of that has nothing to do with it. If whenever you take the derivative of a function, what we're doing is we're taking the derivative of both sides. Whenever you take the derivative of a function, take the derivative of both sides of a function, it's the same as multiplying both sides by d over dx. Implicit, explicit doesn't matter. Even if we never learn this, whenever you take the derivative of a function, you are multiplying both sides by d over dx. And it's cool Leibniz notation. Leibniz notation is the notation. We don't have any Newton notation. It's all Leibniz. But anyways, the notation means something. It's the derivative of this thing with respect to x. It's the derivative of this thing with respect to x. And what does it equal? It equals 1 over x. Yeah, so dy over dx, whatever we want to call it, the y actually jumps up inside. Yeah, it's the same as d over dx. If f of x equals y, it's the same as that, and the y actually jumps up top. Yeah. So the only point, I always have that habit of speaking very technical, over technical about the simplest little thing. Yes, but we're saying that whenever we take any derivative ever, yes, any derivative ever, it's the same as multiplying both sides by d over dx, even if we don't write that. So taking the derivative of both sides is the same as multiplying both sides by d over dx. So that's b. What about c? We have y equals x to the negative 2. Y prime, even though we don't write it, we did just multiply both sides by d over dx. Negative 2, x to the negative 2 minus 1. That's y prime equals negative 2. X to the negative 3. And we do also like those positive exponents. You can bring it down below if you want, where x is not allowed to be 0. Yep, it's just a quick derivative review here. Okay, so all of them are easy, but number 1 is super easy, and then we graduate to easy. Yeah. Okay, so I'm not going to write it, but if we have that, that's our first real chain rule there. If we have that there. I don't know if I said it right a minute ago, but I said that everything is a chain rule. I hope I didn't say product rule. When I said all that stuff, f g of x, what I meant to say is everything is a chain rule, hopefully. The natural log of x is a chain rule. The derivative of tangent x is a chain rule. If you think of everything as a function, all derivatives are a chain rule, including the general power rule. But anyways, so we are thinking about him. Let's just go ahead and take the derivative. The derivative is power out front. The 3 minus 1 times the derivative of the inside. So obviously it's 3 times 2 is 6. 2x minus 1 is 2 equals 6. 2x minus 1 squared, that's the thing. It doesn't get hard, but the power rule, the product rule, I mean, starts there. So let's just save that till the next video here.